Hi everyone, I'm Jason. I work for Facebook, and I've been working on Newsfeed for Android for the past 2 years or so. The whole time I've been working on Newsfeed, I've always had a bit of a focus on understanding the causes of frame rate issues and trying to alleviate any of the problems causing frame rate issues. And this talk is going to be sharing a lot of that information I and my colleagues have learned over the past 2 years, and also giving you enough information so that you can go home and build the same tools that we have at Facebook for identifying problems causing frame rate problems. So first, I'm going to talk about how you can measure frame rate. This is actually pretty difficult to get right. It took us quite a long time to get it right, so I'd like to share that piece of information with you. Also, the metric that we choose to measure frame rate, and it's a metric that we've chosen so that we can identify improvement and regressions, and identify the causes of the problems. And finally, I'm going to talk about how we automatically blame problems that are introducing regressions or skipped frames to the app. And we have a few different tools to do that for us. I'll talk about the differences, the benefits of each of them, and how you can go home and build your own versions of these tools. So let's start with why care. This is a pretty obvious slide. On the left, you have an app that is rendering perfectly smoothly. There might be a frame skipped here or there, but for the most part, it's just really smooth. And on the right, you have the same app, except it's going to be collecting a whole lot of garbage while it's being interacted with. So you can tell that the user scrolls, and while the scroll is happening, the frame just stops for a quarter of a second. Or even sometimes when my finger is on the screen, you could see that the app doesn't respond to my touch in a way that is expected. It doesn't actually move with my finger. And you want that delightful, that pleasant experience of feeling like you're actually controlling the app with your finger and seeing it respond to the things you're doing. So obviously, jitter sucks, and you don't want it in your app. So you definitely want to alleviate this problem. And why does Facebook specifically care about this problem is we have a large number of users on what we would consider low-end devices. These are devices that have 512 megs of RAM, or they have a single core, or a whole suite of problems that could lead to these frame rate issues. So we want to be able to systematically identify all of the problems that are leading to frame rate issues in our app. Before we do this, I'm going to have to get a little bit deep on how Android actually renders these frames. And the reason is because, like I said, it's pretty challenging to get right. And we have to kind of change the way we talk about the problem than what you typically hear in other tech talks. The reason for that is there's a lot of device variance and different options for how you can measure a frame rate. So let's start by just talking about what happens on the UI thread. The UI thread, as we all know, is a pretty special resource. It's the only thread that's actually allowed to render pixels and measure and lay things out. So you kind of want to protect it. The UI thread, when it's rendering a frame, is, for the most part, easily broken down into 3 steps. The first step is handling input. This is responding to touch, or maybe you have a scroll wheel, or any other form of input that the app can respond to. That's the first thing it's going to do. Then there'll be some animation callback. And this animation callback is probably, for the most part, not used in most apps. In games, you'll see it used more often. And there are, if your app is animation heavy, you may also have to do quite a lot of work here. But for the most part, that should be a pretty fast step for us. And drawing is usually the heaviest step. It's where we're actually going to draw pixels and have it ready for the GPU to react with, too. There's also one more important piece on this slide, and that's VSync. VSync is the most important part of this slide. It is a tick, and that means it's going to be happening periodically on a specific interval, and your application will get this tick on the UI thread at that interval, even if you're doing something else. VSync will happen, and it'll be like, okay, what do I do now? It's a recurring quest for a renderable frame. If you have something ready to draw on the screen, you're going to hand that off, and then pixels will actually be drawn to the screen. If you're not ready to draw, that's when you've actually dropped a frame. There's some more complexity there, and I'm simplifying a bit. Project Butter brought along this concept of a 3-frame buffer so that you had a little bit of wiggle room, but I'm going to simplify that for this talk, and you can just know that all of these tools do work and recognize that 3-frame buffer, and they still work. They recognize drop frames. So once you've actually prepared that frame to be rendered, your UI thread can go idle and do other things. There are some things that you may want to do on the UI thread that don't necessarily have to, or sometimes because you're worried about multi-threading and data consistency, you might choose to do a lot of data processing on your UI thread. So during that idle time, you may want to actually use the UI thread for other activities. One note, get used to this. This is going to be showing up in a few more slides. So this is how I'm going to be representing frames being rendered and some motion event or some animation event. So I said we have to kind of change the way we talk about the problem, right? And that's because we always hear this metric of devices trying to render at 60 FPS. 60 FPS isn't actually a perfectly accurate representation of what's happening across devices. Lots of devices don't ever render at 60 FPS. They are capped at a significantly lower frame rate. For example, the Galaxy Core 2 can only measure at 33 frames per second. So if you were to just try and measure in the wild how many devices or whatever metric you choose, how many devices are rendering at 60 FPS, a good chunk of them are just never going to hit that number no matter how hard you try. So you don't want to measure that. You don't want to measure frame rate direct. You don't want to measure against 60 FPS as your goal. And you also have devices that are super, super popular that do try and maintain that 60 FPS, but can either drop or increase their frames per second for a single frame at a time or for chunks of time. While I was actually building this slide, I was testing on my Nexus 5, and I was doing some scrolling, trying to grab some Systrace results, and I noticed that one of my frames took 22 milliseconds to render or something like that. Like VSync was 22 milliseconds apart. Threw me for a loop, took me a few seconds to figure it out, but that's what this talk is about. There's a difference between 60 FPS and skipping a frame. So one interesting metric, 20% of the time, Facebook users, so devices that are currently using the Facebook app, cannot render at 60 FPS because of the device limitation. So the device will either never render at 60 FPS or it's just currently not rendering at 60 FPS. You can access this refresh rate through Android's device object. Device.getRefreshRate will tell you what the device can actually refresh at. We believe that this is fairly representative and accurate. OEMs do seem to be implementing this correctly. You don't want to blindly rely on it, but for the most part, it does seem to be pretty accurate. So you can get a pretty good idea of your user base with this. Now we need to talk about how can you actually measure a skip frame. Like I said, this is pretty challenging to get right. We've been trying to measure this since Gingerbread, and there weren't many good facilities for doing that when Gingerbread was out. So let's just skip to what we do. We use Choreographer. Choreographer was introduced as part of Project Butter in Jelly Bean. It has this very nice utility called the frame callback. And the frame callback's intention is to do frame animation syncing, but we can use it for other things. And it's delivered during the following frame's animation callback. So if VSync happens, that frame callback will be delivered to the next frame's animation callback, and it will tell that next frame when that VSync occurred. You can find how much time it took to render a frame by just measuring the difference between these two inputs. Let's talk about a slightly more interesting example where we're not rendering at a perfect frame rate. As you can tell, there is a dropped frame here. Again, simplifying, but drop frame here. So you have one frame that took 33 milliseconds to render, and we weren't able to draw that frame. So what happens with this choreographer? Well, the first frame gets its frame callback, and then we draw something, and then that timestamp goes to the next frame, and it draws in time also. And that timestamp goes to this other frame, which we weren't able to draw in time, so we drop that frame. And then it comes time to actually draw that frame, and we deliver that timestamp to the last frame here. If you measure the time between these last two frame callbacks, you'll know that it's not 17 milliseconds between these two, and you can safely recognize that we weren't rendering at the fastest possible frame rate for this device. It's super lightweight. I will show you how lightweight it is. This is the interface, and I cut out a lot of Java documentation, but you can get the idea here. The input is the frame time nanos, which is the time in nanoseconds when the frame started being rendered. And the way this is actually implemented is the vsync timestamp that you could have potentially rendered your frame on. So the vsync preceding your frame. This gives you a lot of information. You know when vsync happened. So how could we use this information to actually measure frame rate accurately? Let's build it. We have a frame callback. We have the input, and it's easier to work with milliseconds than nanoseconds, so I'm just going to convert that right out the gate. Your first frame is a little bit special because we don't have anything to compare against, so let's just say, okay, this is the first frame. Let's just know that that's our starting point and post this frame callback again, so we'll be notified on the next frame. For every other frame, you want to know how much time there was between the current rendering and the previous rendering, right? So just compare against the last frame, update your last frame timestamp, and report this to whatever mechanism it is you want to report to. This might be something that you want to do locally on the client. This might just be shooting off some data to some backend. However you want to handle that, you can handle it. And always remember to post that callback again. We're interested in a chain of different frames, right? So you want to keep being notified of that following frame. Once you have this built, it's really easy to make a frame rate measuring API. It's as simple as two methods. You could measure anything with this. It could be scrolling, like we often do at Facebook. It could be animations, like tapping on some button that opens a little flyout. Any animation you want to measure, you can enable by just notifying that this is the first frame, it's that special case, and posting the frame callback. And at the end, remove that frame callback and maybe do some accumulation and reporting, like whatever it is you want to do to that data you just accumulated. This is as simple as it gets. It's really simple to measure FPS for any animation you want with this. So we've talked about how you can measure FPS, and you know that there's different refresh rates you need to worry about. Let's talk now about a reasonable metric you could use. It's a bit of a mouthful. The one we use at Facebook is it's pretty long and hard to describe, but once you understand it, you'll realize why it's useful for us. We worry about the percent of time spent dropping 2 or more consecutive frames. And I'll get into the reason for that in a moment, but first I just want to illustrate what it looks like. You have some 11 frame long animation that you're worried about, and you start off and something in the beginning just drops tons of frames. Maybe you have lots of allocations, you garbage collect, you're handling lots of input, whatever it is. Your second frame takes a ton of time to render and you drop 4 consecutive frames. Then you're kind of recovering from this. You're still dropping another frame, but you're kind of getting back into the swing of things, and then you're smoothing out the animation towards the end. Something to remember, when you drop 4 frames, it actually gets rendered on the 5th frame, the 5th potential frame. So that's 5 frames worth of time spent rendering just 1 frame. If you were to use this metric, 5 out of the 11 potential frames rendered were spent in this 2 or more consecutive frame drop bucket. So 45% of time spent is dropping 2 or more consecutive frames. Why do we use this particularly complex metric? Well, 1 frame drop is noticeable if you're really staring at something and the rest of the app is buttery smooth. If you start where you're not super buttery smooth, that 1 frame drop is going to be completely unnoticeable. And 2 consecutive frames dropped will be a little bit noticeable, and it's kind of annoying. 3 frame drops gets a bit worse, 4 gets a little irritating, and by 5 frame drops, you're not even sure if the app is responding to you when you're trying to do something for a short period of time. And it's just a really frustrating experience. So we want to weight these worse events as more important and bigger problems than these short frame drops. That's why the percent of time spent is important. You get to weight those heavier events. And you also want to be able to track progress even if you haven't gotten perfect yet. So you could have some large GC event, let's say garbage collection takes 500 milliseconds in your app for some reason, and you're iterating on this and iterating on it, and you manage to get garbage collection down to 50 milliseconds, that's a fantastic win. You've improved your app significantly. But you still haven't gotten to just one single frame drop. So you want to account for progress before you've gotten to perfect. And you want to be able to also notice regressions on really bad things happening already in your app. So this gives us that opportunity to dig into events and see how they improve or regress as individual events. So let's get into some fun tools. How does Facebook automatically blame jank? We have one tool which we actually use in production, and this is called Autoblame. Because it's in production, we know that it has to be super lightweight. We don't want to interfere with what the user's doing. We don't want to actually slow the frame rate of the device down by measuring it. And because of that, there's a bunch of little annoying side effects. It has to be pretty high level. You can't be digging in too deep when you don't have much time to do stuff in. It's not going to blame everything. You're going to miss some things. And that's okay, because you can at least blame, if you can at least blame some significant portion of events, you have a pretty good idea of the problems in your app, right? And it's going to be a bit imperfect. Because you're notified of because you're doing all this reporting on a frame callback and it's in the animation step, you're actually reporting things that happen between two animation steps when you're trying to blame a frame. So there's some issues with that. It's not going to be perfect, but it gives you a really good idea of what's happening in your app if you do it right. The way we built this is we have a number of categories. We use 4 different categories in Newsfeed. And these could be things like garbage collection occurring. It could be things like rendering a new view, so get view in a list view. It could be notifying that the data set underlying the list view has changed. These are some of the high-level events that we care about. And when they happen, we just enable some global marker, and we just say, this event happened. And when it comes time to render that frame and figure out how many frames were dropped, if enough frames were dropped, we then try and blame it and say, which of these markers is the most important to us? And in our case, we say garbage collection is the worst. So we say, if garbage collection happened, forget about the rest. Garbage collection is the cause of all of these frames dropped. With that, with this system in Newsfeed, we can account for 60% of slow frame time just using these 4 categories. So it's a pretty substantial amount of slow frame time. It gives us an idea of what the major problems in our app are and where we should focus our time. Let me show you what some of these results might look like on the back end. These aren't exact pieces of data. They've been modified a bit, but this gives you a good idea. First, I want to describe a little open source utility we have called YourClass, which is really awesome. YourClass breaks devices down into small segments that you can actually compare as similar devices. And the way we do that is we say, these sets of devices are considered high-end devices for this particular year. It would have been a high-end device in 2012. It would have been a high-end device in 2014, something like that. And with that, you get to really focus in on classes of devices being affected by certain changes. And you can also see what problems are affecting classes of devices. So garbage collection, as you can see here, is affecting newer devices more than it is on older devices. Whereas get view and notify dataset changed are fairly similar. So how could you implement something like this on your own? Well, we talked about that FPS measuring API. Every single frame, it's just going to do a little bit of timestamp measuring. And you can go at the end of each of those frames and see which of these global markers are enabled. If you dropped enough frames and you want to care about this, then choose the most important one of these markers and clear all the markers, and then let the next frame happen. When it comes time to finally report all this stuff at the end to your backend, then you can just accumulate these percentages of time spent, and you can understand what's actually plaguing your app. This tool was built by Benjamin Jager, who's sitting in the audience, so awesome stuff, Benjamin. Another tool we have, which is really great at digging in further, but we can't use in production because of its overhead, is AutoProfiler. And AutoProfiler uses the sample-based profiling mechanism provided by Traceview. It runs continuously on our continuous integration. We have this awesome continuous integration for performance called CT Scan, and it's basically just constantly updating master and running on bunches of real devices. And this has been talked about in Droidcon London and other places, so you can listen to stuff about that if you want. We have this test running on CT Scan, and it's just constantly running through newsfeed. It opens the app, it has some specific set of stories that we care about, and it just scrolls through them, The whole time it has the sample-based profiler on. And anytime there's a 2 or more frame drop event, we just add a little marker and we're just like, this is the timestamp 2 or more frames were dropped. We might even add some information about how many frames were dropped. With this running continuously, we can pinpoint big areas outside of Autoblame's scope. So, like I said, we account for 60% of slow frame time. That's significant, but it's not everything. We're missing some major problems in the app with Autoblame. This helps us identify that, which is great. We give absolutely no overhead to the user, and we get to find out all the problems that are influencing our frame rate. It also lets us dig into the roots of the problems that Autoblame is telling us is happening in production. So if Autoblame says, well, 40% of the time is spent rendering views and 20% of the time is spent just notifying that the dataset has changed, well, okay, we can dig into notify dataset changed and all of its problems using AutoProfiler. It's a method profiler, so you get to dig into all of the methods and how much time they're all spending. So what would that look like if we were to actually use that information on our backend? This is all completely made up. None of these packages are real. None of these times are real. This is all just made up information, but you get the idea. Say you have some on-scroll event and you realize that, like, holy crap, your scroll listener is taking up an enormous amount of time and we need to fix that. And 16% of slow frame time is blaming to this scroll event in AutoProfiler. Okay, well, what are the high-level actions that are happening inside that? You can dig in and see that, okay, there's some feed logger that happens on every scroll event, some news feed, maybe fetch data, and then some image prefetcher. And the breakdown of these is, well, the feed logger takes 10% out of that 16, the fetcher takes another 3.5%, and the image prefetcher takes 2.5%. Well, maybe there's someone else working on the feed logger, so you're not worried about it. You want to dig into what's happening in this fetcher. Why is fetch taking so long? And it kind of comes back and says, oh, well, notify dataset change is the problem. We're not spending too much time just wondering whether or not we should be fetching right now. That's a pretty fast operation. So let's focus our time on actually improving the performance of notify dataset changed. So you can see how easily this lets you dig into all of the frame rate issues happening in your app for different animations that you care about. It also helps influence trade-offs that you can make. So there are sometimes designs that come through the pipeline where you know it's going to increase frames dropped. And there's nothing you can do to avoid that. It's going to increase frames dropped. How do you determine whether or not it's a good trade-off? So some examples of this, just 2 years ago, if you remember the Facebook for Android app, there was no images loading while scrolling. So you actually had to like scroll and stop on a story just to see your friend's avatar and maybe like the attachments image. And there was no fetching while scrolling. There was no stories being added to the end of your newsfeed until you physically stopped at the end of it. So you'd scroll all the way down, you get to the very end, then we'd like send off the network request to try and fetch some new stories, and then we'd load it all in. Obviously not as pleasant an experience as just infinitely reading, so great design. How much did it cost us? And with AutoProfiler, we have a constant eye on what that trade-off is and where we can be focusing on improvements to keep those features feeling nice. How can you make this at home? This one's quite a bit more complicated than Autoblame, but let's dig into it. You have Traceview, and Traceview has a sample-based profiling option starting on at least KitKat, I think. It may be available before that, but definitely by KitKat, you can use the sample-based profiling. And you can set the sample frequency. 1,000 microseconds is pretty good, so let's just say you stick with the default. There's also the option to use trace-based profiling. We tried it, and I would suggest not using that. It adds so much overhead to the app that you end up not actually testing much in like your 30-second test. So, and it also skews results. So stick with the sample-based profiling on your backend. And in this testing backend that's constantly running this test, how is it going to run this test? Well, MonkeyRunner is great for this. MonkeyRunner lets you interact with an app. It lets you install apps, open apps, interact with those apps by dragging or clicking on things. So it gives you tons of functionality to make your own automated tests. A test, like this is obviously simplification, but this is basically the heart of the test, right? It's deciding to scroll and then pause for a second, and then scroll some more and pause for a second. And it does it a few times, and ultimately you've collected all the data that you care about. That is the animation that we are testing, so that's all it takes really to make this MonkeyRunner script. After you've ran your script, you have this Traceview file dump, you want to post-process that data, because you don't just want to know all of the stuff happening during your test. You want to focus in on the parts that you care about. So eliminate anything that doesn't actually pertain to your problem. And the way we do this is by eliminating anything that doesn't actually belong in a two or more skipped frame event. And the way we do that is, like I said, we have some little marker, and it tells us, okay, more than 2 frames were dropped. Here is how many were dropped. And you can just rip out that chunk of data from Traceview. Then you can send that data to the backend and render it however you feel like would be useful. That part's a lot more complicated, so that's going to be left as an exercise to you guys. Again, another person in the audience here has made that. That's Jingbo Yang. She made the entirety of AutoProfiler. It's awesome. We use it on tons of different tests, anywhere from like simple feed tests to like complicated feed tests. It's great, and it's helped us find lots of problems. To give a little story around this, we were trying to migrate newsfeed to RecyclerView, and we did all this heavy work, and we put out the first experiment and tried it out, and we noticed that the performance was significantly worse in RecyclerView, which didn't line up with our expectations at all with what we knew about RecyclerView's implementation versus ListView. So why is it slower was our question. And we had these tests running already, and we could just pull up some data saying, okay, here's the test running with a RecyclerView, here's the test running with a ListView, and compare the two. And what did we notice? Well, there was like 10% of all slow time spent in the RecyclerView was creating and inflating views. And none of that time was showing up in the list view. So the ultimate problem here was actually just some implementation problem where we didn't account for RecyclerView properly in one of our optimization steps, but it really quickly helped us pinpoint the problem and just helped us pave the way much faster. All right, you've got all these like crazy awesome tools. You know how to measure frame rate. You know how to automate some of the processes. How can you actually go and improve stuff now? Systrace is probably your favorite tool here. Starting with KitKat, you can add custom markers to Systrace. So you can say, I'm interested in tracing this method, and at the beginning of that method, you initialize your custom marker, and at the end of that method, you end it. And then if you run a Systrace, you dump the HTML file, you open it up, and you'll see that custom marker showing up in that HTML file. So you can really play with this and try and improve small chunks of time. You can also use sample-based profiling. It's great. It's fantastic. Again, KitKat and above, I think. And both of these will be super useful tools for iterating. Systrace does have, and I'm sure both of these have the same problem, but Systrace in particular does have a problem that it does have a bit of overhead. So you don't want to iterate on any chunk of time that's too small. The rule of thumb I'll give you is half of a millisecond or more. If something takes half a millisecond or more and you want to improve it, I would suggest adding your own markers to that event happening in your code. Open up Systrace, run the code, cause that event to occur, and then you can quickly iterate on that. And Systrace is obviously only good for something that you can isolate and reproduce. If you know that the very first time an image shows up on your app, you have some performance issue, then you can just open your app, make that event occur, close the app, and then keep iterating on it by doing that. If you're not quite sure what's causing this problem, you first are going to want to find out what's causing the problem, because Systrace does dump a ton of information. You get to look at everything that's happening on all of your threads for any given period of time, and you can obviously try and narrow that down with Systrace's tools, but definitely try and find the root cause first. what can we take away from this? You know how to make some of these tools now, and you could potentially go and build these out if these are interesting to you. But how can you go home and like improve something right now? I'm going to start at the end of the slide. Like I said, find something that, some interaction that you know to be slow. And how you find that, well, I would say that the ideal profiling device right now is probably a Nexus 4. The reason for the Nexus 4 is that the Nexus 4 is pretty old at this point, and it's going to show some of those performance problems that users on low-end devices will see, much more than a Nexus 5 or any of the newer devices will show. So you'll see the problems while you're interacting with the app, and that'll give you a good indication of what the root cause is. Second, I think that the best operating system to do this type of work on right now is KitKat. And the reason is because Dalvik is going to be around for a while. KitKat is an excellent operating system. It's probably going to be something like the new Gingerbread, where tons of low-end devices are going to be made for KitKat. The specs required are pretty low. So you have Dalvik sticking around for a while. You also have the vast majority of your user base right now is still on Dalvik, so it's probably the right virtual machine to be working against. And it's also got a great set of developer tools. Like I said, tons of these tools that I'm talking about only came out either in Jelly Bean or KitKat. So you have tons of tools available to you, and you get to see all of the same problems that most of your users will be seeing. I can't talk about Systrace enough. It is a great way to iterate on a problem that you know to be taking a lot of time in your app. If you've isolated some problem, notify dataset change, for example, cause it to happen in your app and iterate on it. That's the best way you're going to see improvements here. And again, if you're going to be using a profiler like Traceview, I highly suggest using the sample-based profiler. It is significantly better at not getting in your way while you're testing, and also highlighting the real issues with your app over a large enough test. Whereas the method-based profiler might exaggerate certain issues more than they actually deserve to be exaggerated. That's it. Any questions? The question is, how do you keep track of garbage collection events? So at the beginning of any of these events that we're measuring, we just allocate a new object and wrap it in a weak reference. And every frame we're checking if that weak reference still points to a real object. And if not, garbage collection has happened. There's no guarantee from Dalvik or ART that that is actually going to be perfect, but we've found that in production that most devices actually do perform this way, and it's a pretty good representation of garbage collection. So the question is, when you use something like Autoblame and you choose your categories before that test even happens, so you have to isolate your problem before you start the test. How do you? It's like a self-fulfilling prophecy. How do you prevent yourself from worrying too much about these things? Maybe there's something outside the scope of those that you're missing. Absolutely correct. You're absolutely correct. That's one of the reasons why we have tons of different tools to help us figure out where to actually focus our time. And you don't want to blindly follow any one tool, right? You want to validate that the problem you're trying to solve is worth solving, and you should always do that with any performance profile. Yeah, let me go back to this slide because it's really tough to wrap your head around how this works. The question is around this frame callback and if there are ways that can lead to false positives. So you get your animation callback during the animation step of drawing, right? So the previous vsync's timestamp is delivered during the animation step. The timestamps you want to be comparing are the vsync timestamps, not the time that you are receiving this frame callback. And because of that, you're receiving the vsync, in this example, you're receiving the vsync before this single drop frame event, and then the next rendered frame will receive the vsync time after that. So you're guaranteed to get intervals. Let's simplify and say we're talking about a 60 FPS device. You're guaranteed to get intervals of 16.7 milliseconds because it's only going to be reporting vsync timestamps to you. So if you drop a frame, the potentially renderable vsync is going to be a vsync timestamp. Doesn't answer it. No, the question is, what if input here was really small and the animation callback, or the animation step of this was finished in time, and then draw just took a really long time and dragged into that second frame? You still would end up getting the vsync timestamp of the third frame here delivered to the second frame. So it does account for that problem. Yeah, so the question is, does vsync change with the maximum frame rate of the device, basically? The Samsung device that we talked about can caps at 33 FPS, and that means that, yes, vsync will be much longer. There will be more time between each vsync on that device. Because you know how much time there was between those, and you can ask the device for its refresh rate. Yeah. Yes. Am I open sourcing any of this logic? No, not right now. All right. Oh. What are the output formats for our CI? It's pretty complicated. We dump a lot of data for, especially AutoProfiler. You could use XML. All right, thank you guys.